Good morning. I'm Zeynep. I work here at SCCN as a project scientist, and my subject is EEG source localization. So today I will talk about the forward and inverse problem of EEG. So what is the aim? We want to be able to visualize the effective EEG sources on the brain, on the subject's brain surface. So the aim is to have high resolution EEG source activity on the subject's brains. And in order to do that, we need to be able to solve the forward and inverse problem of EEG. So I will give the definitions of forward problem and inverse problem. The forward problem is estimating calculating the potentials and magnetic field, assuming a source distribution inside the brain and conductivity distribution through the head volume. And this can be solved by biophysical equations, and this would give us a unique solution. However, the inverse problem is not unique. We solve the inverse problem by solving many forward problem solutions. So if we represent the scalp electrodes by X, scalp EEG by X, and the volume conductor model by S, and the sources by S, so the minimization problem would give us many solutions. Therefore, we apply electrophysiological neuroanatomical constraints to constrain the sources. And if we look at this problem, the solution of the inverse problem is based on the volume conductor model here, L, and the minimization problem itself. So when we solve these problems correctly, then we would be able to have correct source localization. So, but how do we apply the electrophysiological neuroanatomical constraints? To have some idea about this, we need to know what the generators of EEG. The generators of EEG are synchronous neurons that are active in a patch of cortex that would generate the EEG field. So if we look at it in a bit more close detail, the 2 millimeter thickness of cortex can be divided into 6 layers. And each these layers have different types of neurons and different interactions. And it is believed that the activation of large pyramidal cells of layer 5 is what is reflected in most of the EEGs that we record. So we concentrate on the pyramidal cells. So, however, if these cells are randomly oriented, then the electric current would be cancelled out. Or if they are asynchronously activated, then they will be cancelled out again. So we would need a large number of these neurons that are synchronously activated and parallel oriented to each other so that we can record EEG on the scalp. And I will give an example of this. Here, for example, we have 6 neurons that are not synchronously active. And the resulting current density cancels out. And so we won't be able to read EEG. But if they are synchronously active, then the resulting current would be high. And then this would give us EEG recordings. So when we record the EEG, we realize that the pattern is actually dipolar field patterns. So these can be represented by point-like sources inside the brain, and that would give us recordable EEG measurements. And although the axons have some length, and actually they are line sources, however, the length of the axon is infinitesimally small compared to the distance between the source and the EEG electrodes. So to give a better understanding, so let's assume we have a macro column of neurons here, that the equivalent current source density is represented like this. And then we have hundreds of these, let's assume, on a cortical patch. And that can be represented as a single dipole here, and that would give the recordable EEG. And if there is curvature on the cortex, then the equivalent dipole would be a little bit below the curvature. So if we have multiple sources like this, then we would be getting activity from all these sources on all of these EEG electrodes through the volume conduction. So there is one and another, and this electrode would record from both of these sources. So we can represent the equivalent dipole of this patch like this, and we can represent this one like this, so that it will be all mixed together on the EEG electrode locations. To solve the forward problem, we can use Maxwell's equations using quasi-static approximation. So the quasi-static approximation is that we can neglect capacitive and inductive effects of head volume conductor if the signals are, if the biological signals are lower than 1 kilohertz. So this simplifies the equations a lot. So we only have a resistive conductive model here and the boundary conditions of this conductivity model. So what is volume conduction? So the potential differences between electrodes measures some current flowing through scalp. And only a tiny fraction of brain source currents pass through the skull. So therefore, we need a detailed model of the head for different conductivity tissues. And these tissues are, which have different conductivities, are brain, CSF, skull, and scalp. So we have some problems with skull. First of all, it's the value in the MRI images is 0, which is like the sinuses and vessels. So it's not easy to extract skull from the anatomical images, and the thickness of it varies regionally. Conductivity is not homogeneous, and we have individual skull conductivity for different subjects. And we have recently developed a method to estimate skull conductivity using EEG and MRI, and I will talk about this in the afternoon session. So what kind of volume conductor models can we use? So there are simple head models like spherical or spheroid or multiple layer spheres, or we can use realistic head models, individualized realistic head models from MRI. We can derive it. And so the spherical head models can be, if we use spherical head models, the forward problem can be used by analytical solvers. And this would be really fast and simple, but representing the head geometry with spheres would bring errors in the source localization. On the other hand, if we use realistic head models, then we would need to use numerical solvers. And the most common numerical solvers are boundary element method, finite element method, and finite difference method. But these represent the head shape better, but also these are computationally more complex than analytical solvers. So here are two examples of boundary element method and finite element method. So the boundary element method models the conductivity layers. like brain layer, CSF layer, skull layer, and scalp layer. And the potentials are calculated only on the conductivity layers. Whereas in the finite element method, we model the whole head volume by small elements. We can use cubic elements or tetrahedral elements. So we can compute the potentials anywhere in this volume. I will show some examples of forward problem solutions. So we can have sources anywhere in the cortex. And if we have an activity in this sulcal region, for example, this can be represented by a tangential dipole. And this would give us a really focal tangential potential distribution on the scalp. And if there is some activity in the deep sulcus here, and this can be represented by a deep tangential source, and this would give us a more broader potential map on the scalp. And here are some examples of radial dipoles. For example, we can model this patch of cortex with a radial source, and this would give us a potential map on the scalp, which is focal, and a deep source would give us a more broad distribution of potential map. So the inverse problem, estimating the sources of scalp recorded electromagnetic activity, has been a subject of research for many years. And many methods have been developed in this area. But we can categorize these methods basically in two groups, like dipole parametric methods and linear distributed methods. Where in parametric methods, we are searching for parameters of a number of dipoles. And we use nonlinear optimization methods. And these can be least squares, minimum nonlinear least squares, beamforming, music, and genetic algorithms. In linear methods, on the other hand, we determine the possible source locations, and we search for activation in these given locations. The most common source space would be the cortex. So the whole cortex is modeled by dipoles, and then we search for which ones are active to give out that potential distribution. So these need additional constraints, like the source localization may need additional constraints to have smooth sources, or to have compact sources or sparse sources. And the source space has constraints, like the cortical surface or cortical surface and perpendicular dipoles. So equivalent current dipole source is the most basic source localization technique. We are looking for 6 parameters: locations, direction, and magnitude of dipoles. And here, for example, if we have an active patch of cortex, which can be represented by a dipole, and we are searching for this dipole. On the other hand, the linear distributed methods represent the whole cortical volume with dipoles here. And sources are on the cortex and perpendicular to the cortex. And as we can see here, actually, the lining of the sources on the MRI slice. So in summary, on one hand, we take the MRI and electrode locations and generate a volume conductor model that would give a correct head geometry for conductivity layers, and also the conductivity distribution of the volume conductor model. And on the other hand, we take EEG, ECOG, or MEG signal, and we apply source separation. We separate the sources. And then we solve the source localization for each of these scalp maps. And then we can combine the whole thing with the activations. So the components of EEG source imaging are a forward model, geometry and conductivity distribution, a forward solver, like a numerical forward solver, FEM or BEM, electrode co-registration, EEG source separation, brain source space, generation of brain source space, and then a source localization method. And for these, I have a toolbox, neuroelectromagnetic forward head modeling toolbox, which generates, takes the MR of the subject and generates a mesh for the subject and generates source space and does single dipole source localization. And here I'm showing two BAM models for an adult and for an infant, and the corresponding FEM models for the BAM models for the adult. So NFT generates dipole source localization, or it can do also distributed source localization. So it uses free surfer to generate a cortical model of the subject. So we need to have MRI for this. It takes the MRI, generates the free surfer source space, and then co-registers it with the NFT head model and generate patches of cortex, so the connectivity of the dipoles, and then you can choose the source localization method. Right now I have sparse compact smooth source localization or patch-based SPL source localization. Here I'm showing an example of distributed source localization. Toolbox, here is a scalp map from EEG, and SCS gives a really compact source, and SPL tries to match all the, so the constraint of SCS is to generate smooth and compact sources. So it tries to, so it doesn't do two distributed sources. But the SPL doesn't have a constraint to generate compact sources, so it tries to fit the data at all these, for all these irregularities, so it finds more distributed source locations. I will give an example. I will give an example of inverse source localization for an epilepsy patient that was going under surgery during pre-surgical evaluation. So this patient had a craniotomy, so part of the skull was removed. So I first generated a detailed head model for this patient, modeling also the plastic layer because this doesn't has zero conductivity, so it has to be in the model, and also the hole in the skull, and then the scalp. So this shows the BAM model with the strip and the interhemispheric strip and the ECOG grids. And this is the cortical surface of the patient. So I represented the cortex with 80,000 sources and try to fit the data to find the distribution at the 80,000 source points. So this is the grid of electrodes on the patient's brain. There are 78 ECOG electrodes, and at the same time, scalp EEG was also recorded, 29 scalp electrodes. So the patient had 2 seizures like this, and we first did ICA decomposition, and we realized that this, among the 78 components, 13 of these components were seizure-related. So we first by doing ICA, we first found the seizure activity from the EEG. And we did the source localization for these seizure components. So here are 2 ICs. One of them is if you on the grid and on the scalp. So we merged the data, scalp and grid data, and then did ICA. And then one component actually points toward the head. So this can be represented by a radial dipole. And the other, however, is can be represented by a tangential dipole because it has two polarity here. And we did distributed source localization and represented the cortex with 80,000 dipoles, but also found the patches of cortex with 10 millimeters, 6 millimeter, and 3 millimeter. So we had a source space that's composed of patches of cortex and with different levels. So all these patches were overlapping, and they were 10 millimeters, and at each node there was a 10 millimeter, 6 millimeter, and 3 millimeter patch of cortical activity. So our lead field matrix became 240,000 by number of electrodes. And when we did the source localization, then that radial dipole actually corresponded to a very focal gyrus of the cortex. That tangential component was localized in the sulcus of the cortex. And really, these are focal sources. So after combining, so we have 13 seizure components, right? And we can do source localization for all of these 13 components. And then we can combine them, all these 13 components, and we can have just the seizure, we can visualize just the seizure activity on the patient's cortical surface instead of visualizing the whole EEG. So here I want to give an example of the project. We take the MRI, we did segmentation, and generated the mesh for the subject and the source space. And on the other hand, we take the multi-scale EEG data, EEG and ECOG data, and we did EMCA decomposition, IC decomposition. We filtered the seizure components, and we applied source localization for these, and we showed each component one by one, and then the resulting sources, the 13 seizure sources, on the patient's brain surface. Okay, I'm talking about this volume conductor model. What we should be using. We can generate individual volume conductor models from MRI. However, if we don't have an MRI of the subject, then what happens? We can use template head models, or we can use spherical head models. But what happens if we use template head models or spherical head models instead of realistic head models? What would be the EEG source localization error? And we did this for head modeling. We did simulations to understand the effects of head modeling errors. And we also did the same analysis for co-registration errors. For example, if the subject's electrode locations are, moved a little bit, and what happens if it moves like only 5 degrees? If we should include the white matter or not how much does it affect the source localization accuracy? And we looked at number of electrodes and distribution of electrodes, how much it affects the source localization, and the misestimation of skull conductivity. And among these, head modeling errors does bring, I will show the errors right now. And co-registration number of electrodes, these can be solved by taking pictures or with digitization of electrodes And we can also correct head modeling errors if we have MRI of the subjects. But the misestimation of skull conductivity actually brings huge errors in EEG source localization. I won't get in details of this right now, but I will talk about it in the afternoon session. So I want to show what happens if we don't have MRIs and if we use template head models instead of realistic head models. So we had first a reference head model from whole head T1 weighted MRs of the subject, and we generated a 4-layer realistic band model. And we simulated EEG using this head model. This is the head model for skull, CSF, and brain is shown. And we simulated EEG using this realistic individual head model. And then we solved the inverse problem using different head models, like MNI template head models, 4 layers and 3 layers, and warped MNI head models, because if we have the electrode locations, we have the possibility also to warp a template head model to the electrode locations. So we would have a more individualized head model instead of just using MNI head model or spherical head model. So we solved the inverse problem inside the brain on a 3D grid with approximately 7,000 dipoles that would represent the whole brain area. And for example, this map gives the source localization errors if we use spherical head models instead of individual head models. And the errors are in the cortical region, especially, are up to 2 millimeters when we use spherical head models. And in the basal regions, the errors may go up to 3 centimeters. So this shows the magnitude. The color shows the magnitude of the error, and the arrow shows the direction of the error. Okay, so spherical head model actually is not a very good representation of the head. So we can use 3-layer MNI models that would be more realistic. This also gives some errors, generates some errors. And in the cortical regions, it would be around, so depending on the region, it would change between 5 millimeters to 20 millimeters, the errors. And in the basal regions, again, we have higher magnitudes, because in the individual head model, I used the whole head model, whereas in MNI models are actually down to the nose. So the basal regions have usually more errors than the cortical regions here. And then if we use 4-layer MNI, then we will have less errors. And we can look at the normal MNI or warped MNI actually here. So if we use a warped MNI, which would warp to the electrode locations, and the electrode locations actually gives a representation of the head shape. So we obtain really much improved source localization compared to using normal MNI head models. So even if we don't have the MRI, then we can, if we have the digitizer locations, then we can still have a more individualized head model that would give less source localization error. So in spherical model, the localization errors were up to 3.5 centimeters, and cortical areas up to 1.5 centimeters. And in 3-layer MNI, large errors we had large errors where models do not agree, and this would change from subject to subject. For example, if the person's head is close to an average head model, then it would have less errors, but if the person's head varies too much from average head model, then it would produce more errors. And using 4-layer MNI is similar to using 3-layer MNI, but smaller source localization. We obtain smaller source localization errors. So in summary, if we have MRs of the subject, we can use subject-specific head models. And if we don't have MRIs, then we can use warped 4-layer MNI models. And skull conductivity estimation is as important as using a realistic head model. And we have found out the white matter modeling does not have much effect on source localization. And I have more time actually, so I can give more results about these modeling errors. So here is what we did to understand electrode co-registration errors. We shifted the electrodes by 5 degrees, and when we shift them, the source localization errors were parallel with the shift. I mean, if we shifted like average of 1 centimeter, then the shift in the dipoles were also average 1 centimeter in localization errors. But these are more close to the cortical surface, so actually it has a really affecting error on the source localization. And what about like head tissue conductivities? So for scalp, CSF, and brain, if we look at in literature, then we see very consistent conductivity values. But the skull conductivity varies a lot from person to person, and it varies a lot due to measurement method, and it varies during aging. Young children have very conductive skull. It's not formed yet. They have fontanelles and sutures, but as we age, the skull gets more calcified and the conductivity drops a lot. And there are many individual differences in skull conductivity. So here are 2 examples of measurement methods, and even using like different frequencies in measurement, it would give different conductivity results. And when we look in the literature, so in 1960s, 1970s, the brain to skull conductivity ratio was 80, and we used 80 for a really long time. And then in 2005, then for adults, the brain to skull conductivity ratio was stated as 15, 20, 25. And even there's a study, this one, that would say, 5 for an adult. So for children, it changes even more. So it affects the, so this is the, gives the error distribution. And if we use a brain to skull conductivity ratio of 80 instead of 25, then we get source localization errors up to 3 centimeters. And these errors are very effective because they are all in the cortical region here. And if we use 15 instead of 25, then we would still get source localization errors up to 1 centimeter. So these are really huge errors that we need to overcome. And in my talk in the afternoon, I will talk about how we estimate skull conductivity and EEG source locations using EEG and MRI of the subjects. What about inclusion of white matter? So should we include the white matter or not? So I generated the white matter model from the free surfer using free surfer and included the white matter and solved the forward problem and then solved the inverse problem without the white matter. And the errors were around the in the cortical areas, the errors were up to 5 millimeters. So in the basal areas, so in lower areas, the errors would go up to 1 centimeter. But usually in the cortical region, I mean, it wasn't that significant. And another test we did was the number of electrodes and coverage. So we had 256 electrodes here, and then 128, 64, 32, and then on one side of the head and on both sides of 16 electrodes. So the location errors were, if we use, for example, so this is what we, if we solve the inverse problem with warped MNI model, but if we solve it with only 16 electrodes, then this would produce really large errors. And if the electrodes are located only on one side of the head, then it would be like almost goes up to 5 centimeters. So it doesn't make any sense to have only 16 electrodes. So as a result, in summary, we can have the optimum number would be to have electrodes more than 64 electrodes and evenly distributed on the brain surface. So my summary is, so we need to have, for correct source localization, we need to have an electromagnetic forward head model. And the source localization is estimating the source distribution using the EEG, measured EEG. And we have mathematical techniques that would give us that would give different source localization methods, and to be able to obtain physiologically plausible source locations, then we need to have neuroanatomical constraints in the source location and in the source space. Then search for the most plausible source model. So thank you.